So let's talk about the fundamental theorem of calculus. The fundamental theorem of calculus is very important, hence it's called the fundamental theorem of calculus. There are fundamental theorems of algebra, fundamental theorems of calculus. These are kind of the basics of where we start. And what this says is, the fundamental theorem of calculus says, suppose f is continuous on some closed interval from a to b. The first part says, if g of x equals the integral from a to x of f of t dt, then the derivative of g is just f of x. In other words, just the thing inside. They kind of cancel each other. So that means that the derivative with respect to x of any integral from a to x of f of t dt is f of x, whatever's inside. The derivative and the integral basically undo each other, and that's what this one says. Notice that the a down here is a constant, the x is the variable, and you get f of x. The second part says, we've already actually seen, says the integral from a to b of f of x dx is capital F of b minus capital F of a, where capital F is the antiderivative of little f. This is known as the evaluation theorem. So the other way to think of it is the integral from a to b of f prime of x dx is f of b minus f of a. So we're going to work with these, see how they work. One thing we can do is we can actually find values. So let g of x equal the integral from 0 to x of f of t dt, where f of t is this graph. We want to evaluate g of x for x equals 0, 1, 2, 3, 4, 5, 6. All right, so let's talk about how we would go about doing that. So what we would do is remember that g of x is the integral from a to x of f of t dt. So that's what it is. If we want g of 0, oh wait, I'm sorry. It is actually from f of 0 to x. So it's not just f of a. We actually know that a in this case is 0. So if I want g of 0, that would be the integral from 0 to 0 of f of t dt. We already know that that's 0. We have a wonderful property of integrals to say the integral from a to a of a function is always 0. So we know that one's 0. G of 1 would be the integral from 0 to 1 of f of t dt. So all we do is find out what that integral is. Remember, this is f, this function. So from 0 to 1, remember, integrals are areas under the curve. So from 0 to 1 is this area right here of this function, of this graph. So we just need to find the area under the curve here. We are going from 0, we're going a distance of 1 here, a distance of 1 here. So the area of the whole rectangle, or the whole square in this case, would be 1. We have half of it. So we have half. So this answer is 1/2. So g of 1 is a half. G of 2 would be the integral from 0 to 2 of f of t dt. Again, if we can find out what that integral is, we can find out what that function value is. In this case, we're using graphical methods, but we can also use numerical methods to do this. So in this case, we now have from 0 to 2 would mean we're coming all of this and all of this. So again, all you can do is add these two areas. Of course, this area is below, so you have to subtract this area. So it's this area minus this area. Since they're the exact same because of some symmetry going on here, we know that this answer is 0. G of 3 would again be the integral from 0 to 3 of f of t dt. So coming up here to our graph of our f, that would be, again, taking all this area, plus all this area, plus all this area, or actually minus these two areas because they're below the axis. So remember, these two cancel each other, and we now have half of 1, which is half. But it's below the axis, so it's minus a half. G of 4 equals the integral from 0 to 4 of f of t dt. Coming back up here to our graph, again, we have this whole area, this whole area, this whole area, and now this one too. So again, these two cancel each other. These two also cancel each other. So we're back to 0. G of 5 is the integral from 0 to 5 of f of t dt. So we went from 0 to 1 to 2 to 3 to 4. Now we have from 5. So this is going to equal, adding these all, again, these two canceled, these two canceled. So it's now this 1 plus this half. So 1.5. So 3/2. G of 6 would be the integral from 0 to 6 of f of t dt. So now it's including this one here. So we had these two canceled, these two canceled. This was 3/2, 4/2, well, 3/2, 1.5 plus 2.5 plus 3.5 plus another half. So we have 4. So this is 4. If you want to do G of 7, 0 to 7 of f of t dt, or f of t, yeah. That would mean we now have to figure out what this is. So now we would just approximate what this area is for this part here. Again, we have partials here, so you can just approximate what you think this is. This looks like about 1/4. This looks like a little bit more than 1/2. So maybe 3/4 plus 1/4, that's 1, plus almost 2, maybe 1.9. So we can call that 2.9. Plus the 4 we already had. So don't forget to add in this 4, because again, we add all these up. So here, these cancel. We have this one, plus this one, and then this. So we have the 4 from before, plus this 1.8. So we're actually at 5.8. Approximately, this is an approximation because we were approximating what those areas would be. And as I said, I wanted to estimate what that was. Now, let's say we ask a question, what is G has a maximum value? So where would it have its maximum value? So again, going back to our graph here, here's our graph. We think of this as this is the derivative. So the derivative is positive, so we're increasing, we're decreasing, we're decreasing, we're increasing, we're increasing, increasing. We're still increasing because the derivative is still positive. So the maximum will be occurring at 7. And then we can sketch a rough graph of this. We have the values, we know what they are. So we could actually graph from these points. We could actually now plot these points up and graph this line if we wanted to. I won't bother to do that, but you can kind of get this. You're just going to graph all these ordered pairs, 0, 2, 3, 1, negative 1/2, 4, 0, and so forth, and then connect the dots. Another example is, let's say I have g of x equals the integral from 1 to x of t to the 4th dt. I'd like to find g of x. So again, I'm going to go ahead and do that integral. So you're just evaluating the integral. So the integral, the integral of t to the 4th is t to the 5th, 1/5 of that. I'm going to evaluate that from 1 to x. So we get 1/5 x to the 5th minus 1/5. One would like to find the derivative of g of x, which is the integral from 1 to x of the natural log of t dt. So I actually am asking to find g prime. G prime means find the derivative with respect to x of the integral from 1 to x of the natural log of t dt. Well, by the fundamental theorem of calculus, the derivative of the integral is just a thing inside evaluated at the high point. So it's just the natural log of x. I want to find this one again. I'm going to find this derivative. I'm going to find the derivative of the integral from 0 to x squared of the square root of 1 plus t cubed dr. Sorry, maybe say that again. This is the derivative with respect to x of the integral from 0 to x squared of the square root of 1 plus r cubed dr. And again, the derivative of the integral is the thing inside, the square root of 1 plus r cubed, and this something cubed, and we plug in the x squared, the upper limit. So it's going to be 1 plus x to the 6th, because you remember we multiplied these. There are lots of functions that do not have integrals. They have no algebraic way of finding the integrals. They have integrals, they just don't have an algebraic way of finding them. One of them is the sine integral function. This is actually important in electrical engineering. And so it is the sine function is the integral from 0 to x of the sine of t over t dt. We don't know what this value is, but the integrand f of t sine of t over t is not defined when t equals 0, but we know that it has a limit is 1 when t goes to 0. So we can define f of 0 to be 1, and this makes f a continuous function everywhere. So we can draw the graph of this. But again, we're going to figure out what this integral is. We can do this numerically with your calculator with Desmos. So the first thing to do is to find out what the psi is at 0. We already know that one. That one's 0. We want to find the psi at 1. That would be the integral from 0 to 1 of the sine of t over t dt. So now you would take out Desmos and you would find out what this is. So let me bring Desmos up. So here's Desmos. And I will put in, I want to find the integral. And my integral is going to go from 0 to 1 of the sine of x divided by x. We use sine instead of x instead of t dx. And it tells me that that is 0.9406. So I can now put that value in here, that this is equal to 0.9406. And I can keep doing this. Oops, wrong one. I'm sorry, I went to the wrong place. This is 0.9406. And then I can find the psi at 2. That'd be the integral from 0 to 2 of the sine of t d over t dt. And again, I can do that. And I can go over to Desmos, and I can just change this to 2, and so forth. And I can get that value. And then if I want to, I can plug all these values into a table and have it graph it for me. So I can do that and draw the graph. I'm kind of curious if it will draw it if I type it in. Nope, it doesn't do, oh, it does sort of draw it. Oh, I wanted a T. I wanted T here. Yeah, it will draw it. So it will draw it for me. So it actually is drawing that, and I can actually get what that graph looks like. So this is what the psi function looks like. It basically evaluates at every single one of these points and then draws it up. So there's what that graph would look like. Okay. I can copy and paste in here. I'm not going to this time, but you can do that. You can find the coordinates of the first inflection point to the right of the origin. So again, looking at this graph from Desmos, I can find that first inflection point That's just where it's going to, the first derivative with the second derivative is 0. So we can find that information out. We can find those values out. And you can see it straight from here. You can kind of estimate what that value is. So we can do all this information. Technology is wonderful for us and helps us with that. We can say if this function has any horizontal asymptotes. So again, going back to Desmos, it looks like we may have one at about 1 point something. If I were to make this window a little bit bigger, so let's go to 100. Then you can kind of really see what's going on. It looks like we are in fact going along and getting a value around 1.5, 1.6, 1.58, 1.5, 1.56, 1.58, somewhere in there. We can see that value coming in. So this is a nice feature of Desmos. It's good to use. And you can find that horizontal asymptote. We would like to solve the following equation correct to 1 decimal place. So I actually want to find this value out. So again, I can actually do this with Desmos. I'm going to do this with Desmos. I'm going to actually type in y2 equals 1. And let's try that again. Y equals 1. Okay, there it goes. Didn't like my y substitute. All right, so here's y equals 1. And I can now see that right there is where it crosses. So 0.85 is where I can see that happening. So I can now say that this CB is about x is around 0.85. And again, I get that from my graph in Desmos. And so we can find a lot of information out using this. I want to do one more example. I've did a couple examples with finding derivatives, but let's do one more. So let's find the derivatives. So let's say g of x. Find g prime of x for g of x equaling the integral from 0. And actually, you can have that derivative. So let's make it 1 to x squared of, let's do, we'll do the sine of t over t dt. We'll just use that one again. So I want to find g prime. Again, that's the derivative of the integral. But one thing that's a little different on this one is I actually have not x here. I have x squared here. And so if I have x squared there, it's kind of thinking as an inside function. This is inside the bigger function. If you want to, you can let u equal x squared. And so that would be the derivative with respect to x of the integral from 1 to u of sine of t over t dt. And because we're using u's now, it actually is going to be the derivative of u. So this is equal to, but then because we wanted x, actually I do want an x still there. Because we do want x. That means I need to multiply this. No, I want to do. But we do want the derivative with respect to x. That's where my problem is. Okay. But we do want a derivative with respect to x. We need to multiply this by the derivative of u with respect to x. And that will get me my derivative with respect to x back. So what we need to do is think of this as going to be the sine of u over u times the derivative of u with respect to x. Well, u is x squared. So the derivative of that is 2x. Now, the last thing to do is replace in what u is equal to. U is equal to x squared. And then you can simplify this. So you get sine of x squared over 2 sine of x squared over x. One more I just want to show you. Similar thing, I like to find g prime for g of x equaling the integral from x squared to x cubed of sine of t over t dt. Well, the thing is with this one, this is a little bit harder one to work with. We got to think about this a little bit. We needed to use the fundamental theorem of calculus, we need to have a constant down here, and I don't have a constant. But remember, I can make a constant. I can actually have a nice little property of integrals that allows me to make any constant I want. I'll call it 0. So I can put in a constant, the integral from 0 to x cubed, plus the integral from x squared to 0, sine of t dt. If I add these two integrals together, the integral from 0 to x cubed of sine of t dt, plus the integral from x squared to 0 of sine of t dt, I do get the integral from x squared to x cubed of sine of t over t dt. So great. The only other problem is that I need to have 0 in the bottom. So I need to actually use a property that allows me to change that last one. So I have the integral from 0 to x cubed of sine of t over t dt. Then remember, there's a nice little property that lets me switch the limits of integration to where I can make the x squared on top and the 0 on the bottom. But to do that, it's the negative of that. So I will do the negative of that. Now I'm going to find both of these. Again, we're going to have let's let u equal x cubed. So then we're going to have the integral. We're going to do the derivative now, g prime. It's going to be the derivative with respect to x of the integral from 0 to x cubed of sine of t over t dt minus the integral from 0 to x squared of sine of t over t dt. And then remember, you can do the integral of a difference. You can separate them into two separate integrals. We'll let u equal x cubed. I'll let v equal x squared. Then this becomes the derivative with respect to u of the integral from 0 to u of sine of t dt, sine of t over t dt, times the derivative of u with respect to x, minus the derivative with respect to v of the integral from 0 to v of sine of t over t dt, times the derivative of v with respect to x. We're basically using the chain rule. That's all we're really doing here. It's just a chain rule. You have an inside function, which is the x cubed or x squared, and you have the outside function, which is that integral. The derivative of an integral will be the sine of u over u. The derivative of u with respect to x is 3x squared. The derivative of v, the derivative with respect to v of the integral from 0 to v of sine of t over t dt will be the sine of v over v times the derivative of v with respect to x is going to be 2x. And then the last thing is put in what the u is. So we have sine of x cubed over x cubed times 3x squared minus the sine of x squared over x squared times 2x. And then you're just simplify this. So that gives you sine of x cubed, 3 sine of x cubed over x minus 2 sine of x squared over x. And there's your integral.